Swayam Prabha. Digital India. Educated India.
Welcome back. In today's lecture, we'll discuss about a topic called as IP table lookup. IP table lookup is one of the primary operations the routers in the network need to do. So let's see how does the routers actually do this kind of the lookup operation. What are the complexities involved in the lookup operation and details of that. So we saw last time a diagram similar to this. So what you see here is a bunch of computers and 3 routers, and we said that the IP address table or the routing table in the router looks something like this. So this is a simplified version of the routing table. What you have is a bunch of IP addresses. So this is the IP address number 1. And so if you receive a packet with this destination IP address, you need to send it to this port number. That is the meaning of that. So similarly, if you receive a packet with this destination IP address, you need to send it to the same port number and so forth. So every router in the network actually have such routing tables. The routing algorithms actually periodically exchange information about their neighborhood and connectivity, and then come up with such routing table. And the forwarding operation is basically to consult this routing table and then do the forwarding decision. So where to forward this? So now the question is, what is that it is happening when I say that you need to look into this table and then forward it? What exactly mean by that? What exactly happens inside the router to actually do this forwarding operation? You can see here that on the inside every IP address that are over here are the complete 32-bit IP addresses. This is the IPv version 4 address. So I got a bunch of them, and then the next column shows the port number on which that packet need to be sent to. When I receive a packet, typically it has got 2 parts. The first part is the packet. You have got the header, and then the second component is called as the payload. So every packet has got some portion which is the header part, and the second portion is the payload. Payload we call this is the application data. So on the left hand side you see this header. There are different headers. This is the portion where the actual content is going, that is the payload or the data that is carried inside this packet. And this is from here to here is the Ethernet header, and from here to here is the IP version 4 header, and from here to here is the TCP header. Okay. So in the routing, this is the forwarding decisions that the routers need to do. They operate using this particular header, and particularly the destination IP address which is here. You pick up the bits corresponding to this destination IP address, precisely 32 bits, and then compare that with what is there inside the routing table. So you got these routing entries, and these are all also 32 bits right now, and the destination IP address is also 32 bits, and then you compare. It looks something like this. If my IP address entry is 10.10.10.1010, and you convert this into binary, 0001010 is the first component, this one, and then another 0001010, For the second component, similarly, you got the third one and the fourth one. And when you receive a packet at the router, there are sequence of bits. So this something like this. So this is corresponding to the Ethernet header, and then there are some bits corresponding to the IP version 4 header, and out of that somewhere here are the bits corresponding to the destination IP address. So what it means is I am going to take these 32 bits from the IP version 4 header and then compare it with the entries that I have in the routing table. So every entry is looking something like this in the binary format. I do a string matching by picking the bits from the IP version 4 header to that of the what is there in the routing table. So that's precisely what is the lookup operation. So every packet that arrives, you need to do this lookup operation. So another thing to note is when I say that the packet is actually going from one computer to another computer, let's say my computer is here somewhere say in India, and this has got the IP address 10.10.1.1, and it is going to another computer which is having the IP address, let's say 20.20.1.1, and this packet is routed through a bunch of intermediate routers, and let's call them as R1, R2, R3 and R4, and a TTL value is initially assigned. So let's say this is 32, and every router decrements that TTL value by 1, and here when the packet arrives which is exiting from this computer, so here let's call that as packet P1. So TTL value here becomes 31. The same packet when it arrives here, the TTL values become 30, and when it arrives here, the TTL value becomes 29, and when it arrives here, the TTL value becomes 28. The same and finally with the value of 28, the packet is actually delivered to the destination. This is one part of the operation, and at each router there is a routing table. Here you need to do that consultation process. So every routing table has got an entry like this, and you have some binary sequence and then the corresponding port number, then second binary sequence and corresponding port number, and the third binary sequence, something like this, and then the port number. So every packet when P1 arrives here, you pick up the destination IP address, consult here, compare with this one, compare with this one, compare with this one. Wherever you find the match, you send it to that particular port number. So this operation is happening at every router in R1 and R2, R3 and R4. So one operation is you are decrementing the TTL value by 1 and then sending the packet. And the second operation that the router need to do is to pick up the bits corresponding to the destination IP address and then compare it with the entries in the forwarding table that are there. So now it is obvious that in the last class we said that the network speed is increasing, meaning now we are operating, there are networks links which are capable of transmitting with several Gbps rate. If that is the rate at which the packets are coming to the router, and for every packet I need to make this lookup operation, what is that it takes? So one obvious thing is, as the number of the entries in the routing table grows, meaning, so let's say I have got 100 entries in the routing table. In the worst case, if I am doing a linear search on this table to find out a route or find out a port number on which I need to forward the incoming packet, there are 100 32-bit comparisons that I need to do. And on the other hand, if let's say there are 10,000 entries inside this table, so in the worst case I need to do 10,000 32-bit comparisons. So as the number of the entries inside the routing table grows or increase, you have a lot of work to do. So how does the entries in the routing table grow? When the new people join the network, there are new IP addresses series which are seen. As many as large number of the people join, so routing tables are going to grow in size. So with that, on the one hand, the link speeds are increasing, and on the second hand, the number of the entries in the routing table are also growing. So if that is the case, this is actually going to put lot of challenge on the router. So I need to do the lookup large number of the comparisons, and at the same time I need to do this operation as quickly as possible. So as less time as possible, because the link is actually pushing lot of packets onto the router. And second thing to remember is, when I say this forwarding and the TTL is decrementing, this all operates with the concept called as the store and forward. What it simply means is, the bits on the link are arriving sequentially, meaning if this is my particular packet, and if I start transmitting from the left hand side, this bit is going to arrive first, and then if this is the router and there is a buffer here, and this bit is come and sit here, occupy space here, and the next bit arrives in the next sequence, and that will come and sit in the next position, and the third bit will come and it will sit here, something like this. Sequentially bits are arriving on the link, and they are getting stored inside the buffer, precisely means here it is called as queue. Inside a queue, the bits corresponding to that packet are coming and sitting, and till the entire set of the bits corresponding to this particular packet arrive here, you cannot actually do the processing. So in the worst case, at least the header portion, whatever is there, that portion, all the bits corresponding to that should come. Then only you can do the 32 bits corresponding to the destination IP address should come. Then only you will be able to do the comparison. So at every hop, the storage operation is happening. You receive a packet, store it, then pick up the bits from this buffer, and then go and consult this routing table, and then decide where to forward. So if my destination source is here and the destination is some, let's say 20 hops away, 20 times you need to store the same packet, and then consult the routing table 20 times, and then finally deliver the packet to the destination. That's actually lot of work to do. So 20 different routers on the way actually need to do this lookup operation. So if these routers are not capable of handling these lookup operations, or if they are not able to do this forwarding decisions quite quickly, then the end users, the end-to-end delay would increase. If let's say every router takes 1 millisecond to do that, and if I am crossing 20 millisecond to 20 hops to reach the destination, then 20 millisecond is the time just taken to do the lookup operation, and over and above you have got the processing time, you have got the forwarding transmission time and other things, they will add up. So you will experience a lot of delay during the transmission. So that is actually to effect. So if this is what is happening inside, now the question is, in order to make the or fully exploit the link speeds that are available in today's network, what is that I need to do inside this router to do this lookup operation quite faster? So as soon as the packet comes, I need to do this. I need to do this processing quickly and then send it. So to give just an estimation of what is the kind of the processing that we are looking at. So if you have a link which is operating at 10 Gbps, that will bring approximately 31 million packets per second. So what it means is, in order to process all those forward all packets or fully utilize the 10 Gbps capacity or the bandwidth that I have. So the router need to do lookup operations of 31 million lookup operations per second. That is the scale of the operation that we are looking at. So this is actually quite complex or very challenging operations to do. So the question, we will try to understand how exactly this is done, what kind of the algorithms or mechanisms that I can use inside the router to cope up with this kind of the high speed lookup operation. So before we actually jump into the specific algorithms, let's look back at the history a little bit and then derive some motivation how exactly these routing table entries are organized. I see that in the, at least in this example that I showed, there are these are 32-bit entries. So it is not necessary that the routing table entries, every entry need to be of 32 bits. There are some optimization. If every entry is 32 bits, then the table size, every router in the internet need to have 2 to the power 32 number of the entries. So that's actually quite a large or the huge routing table. And if you want to do a comparison, then you need to do, if you are doing a linear search, then it means that 2 to the power 32 number of 32-bit comparisons you need to do. So that's actually purely is not scalable. So we need to do something than that. So what the network organizers or engineers thought is, let's organize these IP addresses into some kind of the hierarchy and name them into some classes. So class A address, class B address and C address. What it means is, if I am having a network here, and if there are bunch of computers inside, let's call them as H1, H2, so on, Hn, and all these all these computers from H1 to Hn share a common prefix, and that I denote as the network portion of the IP address. So let's say the network portion, if this is a class A address, so what it means is, a class A address reserves the 8 bits which are common for the network and the remaining 24 bits for the host. It is 8 and 24. So the first 8 bits are common for all these n number of the hosts, and the remaining 24 bits are actually varying. So what it means is, if my sequence is something like this, 0 0 0 1 0 1 0, and this is the network portion, and the remaining 24 bits from here to here are the host IP address. So theoretically you can have 2 to the power of 24 number of the different hosts inside this network. So what it means for the routing and the lookup operation is, think of this as case. This is the autonomous system number 2 and this is autonomous system number 1, and there is a router at the border of this autonomous system number 1, and there is a router which is at the border of the autonomous number system 2, and these two are connected with a link. And given that all these hosts inside the autonomous system number 2 are sharing a common prefix of the IP address, which is looking something like this, and typically all the packets which are going to, whether they are going to H1 or S2 or to S3 or to so on Hn, they have to take the same route. If this is the link number 2 and this is the port number 2 and this is the port number 3 for this router, this is R1 and this is R2, and what the router R1 can do is, I don't care really what is this 24 bits host component is, let me build a routing entry with the only the network portion of the IP address, and I will say that every time you receive these first 8 bits or of 1 for 00001010, you need to forward that to the port number 2 or the interface number 2. So, by doing this, what actually we end is the IP address entries or the routing table entries are supposed to be 32 bits, and then we brought them to, it is good enough to store only the 8 bits. So, this will help. By doing this, by a large section of the IP addresses are combined and only one entry for the corresponding to that is actually stored inside the routing table. And similarly, you can think of this. So, if there is a third network or autonomous system and this is using the IP address, let us say 20 dot series, I can create an entry, only one entry for the entire series, and say that you need to forward the packet with the on the interface number 3. So, whatever the common prefix is there, if 20 is the prefix, you come and enter here. So, a bunch of hosts in this network, for all of them, we actually stored only one routing entry in this router R1. So, this will reduce the number of the entries in the routing table. So, that will bring a scale of the operation, meaning that as the number of the entries shrink, you will be able to do the decision quite quickly, because you do not have to search all the routing table entries. If there are only 100, then only 100 comparisons are required. And moreover, what it says is, instead of doing a 32-bit comparison, now I am using class A address, it is good enough to store only 8 bits, only 8-bit comparisons are required. So, by doing this, you can actually to some extent you can accelerate or speed up the operation of the lookup operation. So, that is the class A address. The class A address is identified with the 0, a leading 0, and then the next 7 bits are varying, and then the 24 bits. This is the 7 bit, together this 0 together, this is 8 bits, and the 24 bits are for the host component. Similarly, if there are networks which are not having 2 to the power of 24 number of the IP addresses, you can go for the class B address, which reserves 16 bits for the host component, and then 10 is the which is fixed, and then in 14 bits are reserved for the network component. So, 10 is fixed and 14 bits are actually varying. So, they can take from all 0 to all 1s, these 14 bits. Similarly, class C address is identified by 110, and so this reserves 24 bits, meaning including this 110, and then 21 bits for the network portion, and then the last 8 bits for the host portion. So, if you use class C address, then the maximum number of the hosts that you can have is 2 to the power of 8, and then the maximum number of the networks that you can, distinct autonomous systems that you can have is 2 to the power of 21, and if you use class B, then you use 14 bits, 2 to the power of 14 different number of the networks, and 2 to the power of 16 different distinct hosts within each of those networks. So, that is the So, the question is, if I use class A, then the number of the routing table entries probably that I require is 2 to the power of 8. If I use class B address, then the number of entries, routing table entries in the router is 2 to the power of 16. And if I use class C address, then the number of route table entries would be 2 to the power of 24. 2 to the power of 24 is also quite a big number. So, if assuming if I have a network which is, or the every autonomous system in the internet is actually using a class C address, what it theoretically means is the routers which are here, every router which is in the border or connecting two autonomous systems need to have 2 to the power of 24 number of the entries. That is actually huge. So, this is 2 to the power 24 entries here, 2 to the power 24 entries here, and so forth. So, again, as the number of the hops between the source and destination increase, the searching time at each hop would going to increase. Now, one aspect is I want to put this number of the entries in the routing table within the limit, and that's why you want to do some optimization. That is one aspect of the one optimization that I want to bring. And the second thing is these classful addresses are actually kind of wasting the IP addresses that are available for utilization. So, if let us say if this autonomous system is using the class B address, which is 10, and if it does not have 2 to the power of 16 or the number of the host, let us say it has got only the 1000 host, then the remaining sequence of the IP addresses which are part of this series would not be utilized, they go waste. So, in order to avoid this situation, what the network designers thought is, let us not fix the IP addresses, the range, what is this is the network and this is the host portion, and let me make it variable. So, that is the concept of something called as the classless inter-domain routing. In short form, this is called as the CIDR. So, there are every autonomous system or the every network has to decide, depending upon the number of the hosts that are going to be part of that network, what portion of the 32-bit IP addresses I am going to give it for the host, reserve for the host component, and what portion of the IP address I am going to reserve for the network portion. So, what it simply means is, instead of saying that this is a class B address and I require 16 bits for the network, what you can say is, I have some X number of the host, I require 26 bits for the network and the remaining 6 bits for the component. That is the division. So, 2 to the power of 6 is the number of the host that there. So, somebody else can say that I am going to have 18 bits for the network and the remaining 14 bits for the host component, and then you can have 2 to the power of 14 number of the hosts inside that network. So, if the number of the is for the network portion is not fixed, what it means is the routing table entries are also not going to be of the same size. So, if everybody was using the 8-bit network IP address, then the entry will also be 8 bits. But what we are saying is, now one can have 26-bit prefix, the another can have 18-bit net ID. So, what it means is, if I am the router, then my forwarding table, the entry number 1 can have 26 bits and the entry number 2 can have 18 bits and entry number 3 can have 14 bits and something like this. So, within the routing table, the different entries can have different number of the bits stored inside the table. Every entry is of the different size, that is possible. So, in that case, my comparison what I want to do are going to be even more complex. So, you do not have any alignment, meaning that I am not saying that you do only the 8-bit comparison, you do only the 16-bit comparison, you do only the 24-bit comparison and so forth. So, one is 18 bits, another one is 26 bit, another one is 14 bits. I need to do a variable number of the bit comparisons within routing table, and moreover, it is possible for the networks to have one entry which is 32-bit, which is more specific to a particular host, and another entry for the same network with the prefix stored inside network. What it means says, so if let us say 10.10.10.10 is the IP address, this is the exact 32-bit IP address, this is the entry number 1 in the routing table, and the entry number 2 might say that, so this you forward it to port number 2, and anything that is having starting with 10.10, and I do not care what are the 16 bits are, and you forward it to port number 3 or port number 2 itself, whatever it is. So, this is possible. Then when I am doing the search operation, when I am doing the string matching, comparing the 32 bits, so whether if I find a match with this one, I should go with this one, or I should go, one is saying that you should forward it to port number 2, and the second one is saying you should forward it to port number 3, whether to follow the second routing table entry or the first routing table entry, that is the question. And the answer to this is, the routers are supposed to do a longest prefix matching, meaning that if I find an entry in the routing table which is the maximum that is matching with respect to what I have as the destination IP address, you follow that. So what it means is, in this case, if you receive a packet which is supposed to go to the destination 10.10.10.10, and then although this is a valid match, so but the longest match is this entry, you forward this particular packet to port number 2. And what it means is, a consequence of this is, so I might have a large number of the entries given one destination IP address, the 10.10.10.10 can match to multiple number of the entries in the routing table. So meaning that one is saying exact 32 bits, you forward it to port number 2, and the second is saying if the IP address is starting with 10.10, then you forward it to port number 3, and the third one might come back and say if the IP address is starting with 10, then you forward it to port number 4, something like this. So it is not good enough to do the comparison and you find a match and then do the forwarding. So I should keep continuing to do the matching and find the best possible match for this particular destination IP address, and using that I am going to do the forwarding decision. So that is the thing. So although I might have, let's say my number of the entries in the routing table is n, and I start comparing, picking the destination IP address, I start comparing entry number 1 and 2 and so forth. If let's say 10th entry is matched, it might be a fraction of that, it might be in this format 10.10, and then you forward it to 3. Although this is a valid match, I am not supposed to stop the search operation or the comparison operation there itself. I do not know, there might be subsequent entries which are more specific and it might match more number of the bits than just the 10.10. So in that case, what is the possibility? In the worst case, what can happen is, so you need to compare that every packet with every n number of the entries inside the routing table. So that is actually going to put load on the router. So every time, if let's say I receive the packets and most of the packets are able to find a route in the first 10 entries, then although I might have 1000 entries subsequently, if I am not searching them most of the time, 99% of the time, then that is a substantial reduction in the searching work that the routers are doing. But that is not happening here. So you need to continue to do the searching till you find the best match. So I don't know where is that best match, so that's going to complicate. So you need to search all of them. That brings us to the concept of something called as the prefix based routing. So in effect, what we said is, if I am saying that my network address is 16 bits, the routing table entries are 16 bits. So if it is starting with 10.10, and then what I can do is, I can denote that or the entries inside the routing table using this prefix notation. 10.10 star is actually a prefix notation. So all the classful addresses for that matter, when I said that class A address is starting with 0 and then the next 7 bits and then the 24 bits for the host portion, this I can represent in a prefix format in this something like this. So maybe 10 star is the prefix, so that is the address, and then if I am using the class B address, then the these are, this is 10 and then the next 14 bits and then the 16 bits. So that might brings us to the top. I might say that this is 10.10 star, and if I am using the class C address, then this is 11 0 followed by 21 bits and then the remaining 8 bits. So the prefix might look like 10.10.10 star. So all these are appearing in the form of the prefix, and so is the CIDR entry, something which is written as 10./16 would corresponding to a prefix which is 10 or 10 or star, and something which is written in the format of 20.20/16 would mean that 2020 star. So every address, whether you use the classful addressing scheme or the classless addressing scheme, so depending upon the network portion that is available, I can denote that in the form of the prefix. So what it means is, when I am doing the search operation, I am actually doing the search operation on the prefix notation. The routing entries are in the prefix format, and the comparison also done by taking the what it means is, when I say /16, you ignore the next 16 bits, pick up the first 16 bits of the incoming IP address, the destination IP address, and then you compare it with the entries inside the table. So that's how the comparisons are done.